Okay, today we're going to be working on the last two aspects of truth tables that we want to deal with. We're going to talk about the corresponding conditional, and then we're going to move into indirect truth tables. I think the corresponding conditional is pretty painless. The indirect truth tables take a little bit of work to get used to them, but yeah, I guess it's not too bad either. Let's get started with corresponding conditional in 3 easy steps. Step 1, you're going to convert your single slashes, your premise separators, to dots, and your double slashes or your conclusion separators to horseshoes. So in this argument that we have set up on the right, we have P horseshoe Q slash P double slash Q. We're going to convert the single slash to a dot, and then we're going to convert the double slash to a horseshoe. There's that first conversion. Then the step 2, you're going to make the new horseshoe. So in this case, we have two horseshoes, but the first horseshoe on the P horseshoe Q is the old one. That's already been there. The new horseshoe, so that converted double slash horse that you made into a horseshoe, that one is going to be your main operator. So you just have to enclose in a way that makes that happen. In this case, we're going to enclose premise 1 with the parentheses. And then we're going to enclose premise 1 and premise 2 together with a square bracket. And now you have the horseshoe, which had replaced originally the double slash, that's functioning as the main operator of your argument. And then you're going to solve the statement like we're used to doing. So I'm going to pretend the key is already there. Hopefully you're comfortable with the keys by now. We'd use we have two separate letters P, Q, so we're going to use 4 rows. There's going to be 2 and 2 for the truth values of the P, and then it's going to be every other one for the Q. And then we'd plug that in. And then we solve our statement. Before we do that, I'm going to clean some of this up. So we're going to just have that third row down that has our new square bracket in the parentheses, and the horseshoe is the main operator. So we'll turn this into black, and then we'll get rid of the old stuff because we don't need that anymore. This statement that we're looking at right now, square bracket, parenthesis, P horseshoe Q, close parenthesis, dot, P square bracket, horseshoe Q, that is the corresponding conditional. So we've converted the argument into a conditional statement. And so that's why we call it the corresponding conditional. It's the conditional statement that corresponds to the argument. Next step, we're going to plug in our truth values. So I'm going to assume here that we're all confident with our truth table, with our key for our truth tables. So we have square bracket, parenthesis, P horseshoe Q, close parenthesis, dot, P, close square bracket, horseshoe Q. I see two letters here, a P and a Q. So that's going to be 2, L equals 2 to the nth power. That's going to be a total of 4 rows. And under P is going to be 2 trues and 2 falses, and under Q is going to go true, false, true, false. So let's go ahead and plug those in. Next step, you finish solving this out. You start most enclosed and you slowly work your way out. So P horseshoe Q, we have the horseshoe is a true true is a true with a horseshoe, true false is a false with a horseshoe, false true is a true with a horseshoe, and false false is a true with a horseshoe. So here's the plugin for that. Then we move to the next one is the dot operator that's going to evaluate the horseshoe with the P. True true is true, false true is false, true false is false, and true false is false. So there's that plugged in. And then the final step, we're going to evaluate the dot with the Q to give us the horseshoe, and the horseshoe is our main operator. So you have true horseshoe true is true, false horseshoe false is true, false horseshoe true is true, and false horseshoe false is true. So this is true, 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 true all the way down. And now we're done we're done solving through the truth tables. In the final step, we have to evaluate. So what you do is you look at your main operator. If your main operator is a tautology, the argument is valid. Otherwise, so in other words, if it's self-contradictory or contingent, it is invalid. This one's a tautology, so it's a valid argument. In order to see why this works, let me go skip ahead to another argument, show you what an invalid argument looks like. So if we have P horseshoe Q slash Q double slash P, I'm going to do its corresponding conditional as well beside it. So you have P horseshoe Q. We're going to replace our single slash with a dot. We're going to replace our double slash with a horseshoe. So we just took that single slash, turned it into a dot. We took the double slash and turned it into a horseshoe. Then we need to make the horseshoe the main operator. So we'll take the premise 1. We're going to put that in parentheses. And then we're going to put a square bracket around both of our premises. And now we have the horseshoe is our main operator. Now I'm going to solve both of these side by side. So we have true, true, false, false, true, false, true, false, true, false, true, false, true, true, false, false. Same thing over here. True, true, false, false, true, false, true, false, true, false, true, false, true, true, false, false. Continue solving. So P horseshoe Q is going to be true, false, true, true. We don't need these anymore, so I'm going to get rid of them. Okay, for this corresponding conditional, we have true, true is true, true, false is false, false, true is true, false, false is true. We don't need these anymore. Okay. This is where the move to the corresponding conditional, we need to look at some comparisons. So for the argument to be invalid, we need to find a case where we have all true premises and a false conclusion. We have here a true premise, true conclusion. That's okay. We have a false premise. That's okay because we're looking for all true premises and a false conclusion. Here we have a true premise. This might cause a problem if we have a false, and a false conclusion. So this row tells us the argument is invalid because it allows for all true premises and a false conclusion. Allows for all true premises and a false conclusion. Okay, so there's our problem. Well, if you go to your corresponding conditional, the time you're going to have a problem, let's take a look at it. So true dot, we're going to finish solving this through. True dot true is true. So remember, we're evaluating this horseshoe and the Q. False dot false is false. True dot true is true. True dot false is false. Then we evaluate the dot and the P to give us that last main operator horseshoe. So dot is true, P is true with a horseshoe is true. Dot is false with P is true with a horseshoe makes it true. Dot is true, P is false with a horseshoe makes it false. Dot is false with P is false and the horseshoe makes it true. Okay, so here's the big deal with this. If you focus on your main operator for the corresponding conditional, if your main operator, in this case the horseshoe, is a tautology, if all of the truth values are true, then the argument is valid. If they're all false, the argument is invalid, and if they're contingent, which means at least one is true and at least one is false, the argument is invalid again. So the only time it's valid is when all of these truth values under the main operator column are true. In this case, you have a false on your third row down. And so that tells us that the argument is invalid. Now, if you notice, the third row down is also where we had the problem for the old school truth table method of evaluation. What's going on with the corresponding conditional is that if you have all true premises, the conjunct will be true. And so what you're looking for then is, do you have a true left side of your horseshoe and a false right side of your horseshoe? If you have a true left side and a false right side of your horseshoe, let me erase these circles that don't matter anymore. If you have a true left side of your horseshoe and a false right side, your horseshoe is going to be false. So if you have an invalid argument, in this case we have a two premise argument, If it's invalid, you need to see all true premises and a false conclusion. If you have a false conditional, which in other words is going to tell us the argument is invalid, you need to have a true antecedent and a false consequent. That would make the statement false. Well, that true antecedent, remember, was our conjunct, which connected our two premises together. So this really means all true premises. To have a true antecedent with a corresponding conditional, you have to have premise 1 true and premise 2 true because they're combined with a dot. So a true antecedent means all true premises. And then if you have a false consequent, that's going to be a false conclusion. So your false conclusion is your consequent, your true premises is your antecedent. In order for an argument to be invalid, you have to have all true premises. Well, that's just the same thing as saying that antecedent is true and a false conclusion. And that's the same thing as saying that consequent is false. So the very same condition that makes an argument invalid, all true on the premise side, false on the conclusion side, is the same thing that makes your conditional statement false, all true on your antecedent side, false on your consequent side. So conditional statements kind of, in a way, share a property with arguments, which makes the corresponding conditional effective mode of evaluation of arguments. So it's just another way of evaluating arguments. Now, there's a third way of evaluating arguments, and it's kind of a shortcut for all of this, and that's going to be called the indirect truth table method. Let's start working on that. So indirect truth tables. Step 1, you're going to assume your premises are true and your conclusion is false. Step 2, you're going to ask a question. Can you consistently plug in truth values for your letters, keeping true premises and a false conclusion? Once you call a letter true or false, it's got to stay that way everywhere else. So you can't call something, if let's say you have P horseshoe Q, wedge P. If you call P true in one place, you have to call it true in the other place. You can't call it true one time and false somewhere else. That's what that means. Step 3, if you can do it without a problem, in other words, keep your premises true and your conclusion false, and plug in truth values for all of your letters, if you can do that without a problem, and a problem would be you'd have to call a letter true in one place and false somewhere else, the argument is invalid. Because remember, you're up here, you're trying to create all true premises and a false conclusion. Well, if you do have true premises and a false conclusion, that can't be a valid argument. So if you can make all this happen, if you can make true premises and a false conclusion, and you don't encounter any problems, the argument is invalid. If you do run into a problem, or you can't do it without a problem, the argument is valid. So no problem equals invalid. Problem equals valid. With one side note, sometimes you're going to have to try to find a problem more than once. And that's going to be situations where there's a couple different ways you could make a operator true or false. We'll look at an example of that in just a second. So let's go ahead and practice with this indirect truth table method. Step 1. So we'll look at this argument. P horseshoe Q, P / Q. Step 1, we're going to assume that our conclusion is false and our premises are true. Step 2, we're going to plug in truth values to make all of this work out. So if we have a false conclusion, Q has to be false. If we have a true premise, well, P has to be true. And if P is true, and we have a true premise here, if P is true, and you have a true premise here, Q would have to be true as well, because if Q is false, then you'd have a false premise there, and we don't want that to happen. So Q has to be true. But look, we already called Q false in our conclusion. And so we have a problem. We cannot consistently make all true premises and a false conclusion. We hit a problem. And we can't get around that problem. So the argument is valid. If you can't get out of that problem, the argument is valid. If you can do it without a problem, the argument is invalid. We hit a problem, which means we cannot make this come up with all true premises and a false conclusion. Let's look at a second one. P horseshoe Q, not P, therefore not Q. Okay, so in this case, we're going to try and make true premises and a false conclusion. In order for this conclusion to be false, Q needs to be true so that its negation, the main operator for this conclusion, is false. If Q is true here, we have to carry your Q. You have to carry the true Q over to the first premise where it's P horseshoe Q. Now, if your consequent is true, your antecedent might be true, it might be false, it doesn't matter. And so rather than deal with this premise anymore, we're going to move over to the second premise, because the second premise, we want it to be true, but there's only one way it can be true. And that's if P is false, and then its negation makes it true. Now, if you call P false in the second premise, you've got to call P false over in the first premise as well. And if you have a false antecedent and a true consequent, well, that's a true statement. So here, you had no problem making this happen. So the argument is invalid. Because it allows for all true premises and a false conclusion. Okay. One more time, I'm going to rewrite an argument that is this. Remember, this one was, so this one is invalid. One more time, I'm going to write a valid one above it so you can see the difference. So we have P horseshoe Q. In this case, I'm going to call, rather than the earlier time we said P was negated, this time we're going to negate Q and say therefore negation P. So we want to make true premises and a false conclusion. In order to make negation P false, we have to make P true, then its negation is false. Carry the P over to the first premise as true. Now, if you want your horseshoe to be true and the antecedent is true already, your consequent has to be true. Now you have a true statement there. Well, if your Q is true, you have to carry that same true over to your second premise Q, but when you negate it, that negates to a false. But we want that premise to be a true premise, so Q can't be true here. Q has to be false here, but we just hit a problem. We want, in order for these premises to both be true, Q has to be true in one place and false in another. And there you've bumped into an inconsistency. And so here you cannot make it happen. You have a problem making it happen, and so the argument is valid. Valid because cannot make true premises. And false conclusion. Okay, so the difference between this valid one up top and the invalid one below is the valid one up top, you hit a point where you're going to have to call a letter true in one place and false in the other. But down below in the invalid argument, all of the letters, so you have P, it's false everywhere. Q is true everywhere, so the letters keep their truth value the same everywhere they go, and you get all true premises and a false conclusion. I'm going to draw the long truth table for this invalid argument on the bottom so we can see a little bit more detail of what's going on with this indirect truth table. Okay, so we have P horseshoe Q, negation P, double slash negation Q. Under P, we're going to go true, true, false, false. I'm going to assume we're all confident with the key, and I'm just going to start plugging in that key. But we would do a PQ on the left and set up the key, but I'm just going to keep going with it. Okay, so we got that set up. Now when we solve, the negation P is just going to go from true, true, false, false to false, false, true, true. And P horseshoe Q, true, true is going to be true, true, false is going to be false, false, true is going to be true, false, false is going to be true. And then the final step for evaluation, you have to negate your Q. So we'll go false, true, false, true. Okay, now for evaluation, remember for the long truth table, we're looking for a true premise, and a false conclusion. We're looking for all true premises and a false conclusion. If we see that, the argument's invalid. If we don't see that ever, the argument is valid. The main operators we're focusing on is the horseshoe and the two negations. So let's go through one row at a time. The first row, you have a true premise, a false premise, so there's no problem there because we want all true premises. The second row, you have a false premise, no problem there because we want all true premises. The third one, you have a true premise, oh, and a false conclusion. That does give us all true premises and a false conclusion. So there's our problem. Let's look at the last one just to be sure, see if there's another problem. The last row, you have a true premise, and a true conclusion, so there's no problem there. Okay, so this is the old model of truth table evaluation, and we did find all true premises and a false conclusion. Right here's your false conclusion. Remember, it's the negation for the main operator of that conclusion, and it's the negation is the main operator of this premise, and it's a conditional, or the horseshoe is the main operator for this premise. So you have a true premises and a false conclusion, and that tells us the argument's invalid. Well, if you look at your indirect truth table that we did a minute ago, look at the truth values. You have a false, a true, and a true for your horseshoe. Now go over to your main, the old version of the truth table. You have a false, a true, and a true for the truth values for your truth table for the first premise. Then if you go to your second premise on your indirect truth table, you have a true and a false. Go to the second problematic premise for the old school truth table, you have a true and a false. Then you go to your conclusion of the indirect truth table, you have a false and a true. Go to the conclusion of the old school truth table, you have a false and a true. So what the indirect truth table does is it forces this problematic line to show up. Let me erase the other rows so we can see these two side by side. So get rid of row 1, get rid of row 2. We're going to keep row 3 because that's the one that gave us a problem. And if you look at these two rows side by side, you have false, true, true, false, true, true. That matches true, false, false. That matches false, true, true. That matches. So the indirect truth table, once again, just kind of forces the problematic row to show itself for your argument. That's a pretty interesting way of kind of shortcutting the long truth table method. It takes some practice, but it's a cool way of going a little bit quicker. Let's go ahead and look at another example. So we have an argument B horseshoe C and negation C, therefore negation B. So step one, we're going to assume our conclusion is false and our premises are true. And then we're going to try and plug in truth values for the letters to make this all work. So if the conclusion is false, we need B to be true, so negation B is false. We're going to carry the truth value of B over to your first premise, so that's going to be true. Now if B is true, and this has to be a true statement, C has to be true as well. C has to be true as well. Now you have a true premise there. But if C is true here, you've got to carry it over to your second premise, but we hit a problem. Because if C is true, the negation of C is false, and that main operator tells us the whole premise is false. So in your second premise, C has to be false in order for it to be negated to a true for a true premise. And so we have C being true and false, and that's our problem. So we hit a problem that we can't avoid. So the argument is valid because we can't make all true premises and a false conclusion with this argument. It just doesn't work because at some point we're going to have to call C both true and false. Now, what we're going to have to do in a few occasions is evaluate a problem more than once. For instance, this is going to be a long one. M wedge in horseshoe O. Premise 2 is going to be O horseshoe parenthesis N wedge P. Premise 3 is going to be M horseshoe parenthesis negation Q horseshoe N. Premise 4 is going to be Q horseshoe M horseshoe negation P. And your conclusion is going to be N triple bar O. Let me get those parentheses set for that last premise. Okay. So the triple bar statement can be made false in two different ways. And so we might go through the first way and hit a problem, and then we'll just have to reset and go through the second way and see if we can't make everything work without a problem. Let me walk you through this. So premise 1 we want to be true, premise 2 we want to be true, premise 3 we want to be true, premise 4 we want to be true, and the conclusion we want to be false. Okay, so we're going to try and plug in our letters so all this works. If we have N is true and O is false, that makes the triple bar a false statement. So let's go through and plug in trues for all of the N's. There's a true there, there's a true there, there's a true there. And now for the O's, we're going to plug in falses. There's a false here, a false here, and that's it. Okay. Right away, there's a problem. If you look at this first premise, if you're trying to make that true, but you've already called your O false and your N true, you can't make this premise a true premise, because if you plug in a true for your M, that wedge is true, and then the horseshoe is going to be false. That's if M is true. If you make M false, because the wedge, if one side's true, the whole thing's true, that wedge is going to be true again, and then you have a true false for your horseshoe, that's going to be false again. So you cannot make this first premise true if your conclusion has a true on the left and a false on the right. So you hit a problem. Remember, if you don't find a problem, the argument's invalid. If you do find a problem, you might have to try again. And in this case, we have to look at the other combination that will make your conclusion false. So this time, let's call N false and O true. That's still a false statement. I'm going to erase or cross out the top one so we don't confuse ourselves as to what we're dealing with. And now I'm just going to erase it. So we want N to be false. I'm going to rewrite it up higher. We want N to be false and O to be true. Okay, so we'll plug that in everywhere else. N is false, O is true, O is true, N is false, N is false, and that's it. Okay, starting with, let's see, the second premise we have to work on right away, I think, because you have a true antecedent, and in order for that whole statement to be true, you have to have your consequent be true as well. The left side of your wedge is false already, so in order to make this wedge true, you've got to make P true. And now you've got a false wedge true is going to be true, and a true horseshoe true is going to be true. So P has to be true for this statement. So that's going to make your wedge true, and that'll make your horseshoe true. So your second premise is good. Now we plugged in P as true, so let's find any other P's. Over on the last premise, you have a P, so that's got to be true. Now that's going to negate to a false. Now we can stay with this last premise a little bit longer, because if we want your horseshoe to be true and you have a false consequent, let's take a look at that. So we have the horseshoe as P, Q, P, horseshoe, Q. This is the truth table operator definitions we worked with a long time ago. True, false, false, true, false, true, false. This is only false when the left side is true and the right side is false. So look here, if we already have that negated P as false, so we're saying the right side is false, we have to make the left side false as well for that whole statement to be a true statement. So we have to make Q horseshoe M false. Well, what does it take to make Q horseshoe M false? It's going to take Q being true and M being false. Now that's a false statement, and that's the antecedent of this main operator of your horseshoe of your last premise. And so you have a false. So now this, you have a false, and a false gives you a true. And so now we did consistently make this last premise true. But in order to do that, we had to call M false and Q true. So let's plug those in. M is over here. I have it as false. Q is true. There's a Q, and that's true. Okay, so this last premise, it works out. We have two more premises to go. Let's see if we can make those things work. The second to last premise, oh, M, we didn't plug in the last M for the first premise. So there we have M is false as well. Okay, so let's see, does this work? If the second to last premise, you have Q is true, the negation makes it false. It is false of the negation, and the false of the N for your horseshoe makes that a true statement. And then our main operator, we're going to evaluate the false of the M with the false of this horseshoe here. False, horseshoe, false is true. So we did make this one true as well. So we have the last three premises are all true with no problems. And then our first premise, if M is false, N is false with a wedge, that makes it a false statement. And then if you have a false horseshoe true for your main operator, false horseshoe true is a true statement. Remember, that's this third row down on your old school operator definition. False horseshoe true is a true statement. And so the first premise works as well. And so you did make, it took 2 tries to make it happen, but you did make all true premises and a false conclusion. So this allows for all true premises and a false conclusion. So it is invalid. So we finally hit all true premises and a false conclusion without a problem, so it's invalid. So one more time, if you don't have a problem, the argument's invalid. If you do have a problem, try again. I'll write that down. If you don't run into a problem, the argument is invalid. If you do run into a problem, try a different way. If there are no other ways, and you always hit problems, the argument is valid. So if you don't run into a problem, the argument is invalid. If you do run into a problem, try a different way. If there are no other ways and you always hit problems, then you can say the argument is valid. So that's the indirect method for evaluating truth tables. Go ahead and get working on your homework, and I'll see you next time. Take care. So we look at our main operators, and we're looking for all true premises and a false conclusion. The main operator is going to be the horseshoe in premise 1, the negation in premise 2, and the negation in the conclusion. In premise 1, we have a true for the first main operator. In premise 1, we have a true for the main operator. In premise 2, we have a false. So no problems there because we want all true premises. Remember, we want true, true, false. We want all true premises and a false conclusion. Premise 2, we have a false. We want all true premises and a false conclusion. No problem there. Premise 3, we have a true premise. Oh, but our conclusion's true as well. Remember, we want all true premises and a false conclusion, so no problem there. In our conclusion, we have a true premise, and a false conclusion. There we have our problem that tells us the argument is invalid. Now, I'm going to erase the 3 premises. Now, if we go back to our indirect truth table, what we see is, oh shit.